All right, let's jump right in. You ever look over a chemist's shoulder and see all those weird lines, zigzags, and hexagons? It kind of looks like they're writing in code, right? Well, in a way they are. And today we are going to crack that code. We're learning how to read the blueprints for the very molecules that make up, well, everything.
So, this right here is the big mystery we're solving today. How in the world does this super detailed, maybe even a little messy drawing on the left become this clean, simple zigzag on the right? Believe it or not, they represent the exact same thing. It looks like a huge jump, I know, but trust me, by the end of this, you'll see it's actually pretty simple.
So here's our game plan. Think of it like a level-up journey. We'll start with the absolute basics, then we'll learn some chemical shorthand, then we'll master the tool the pros use, and finally we'll take the leap from flat 2D drawings into the real 3D world where molecules actually live. Ready? Let's go.
Okay, section 1. So why the big secret? Why do chemists need this special language anyway? Honestly, it just comes down to saving time and space. I mean, can you imagine drawing out every single atom for a really complex molecule? It would take forever and your notebook would just be a giant mess. So yeah, they needed a better system.
This slide is perfect. It lays out our whole journey. We're starting at level 1, what I call the literal drawing, where you see absolutely everything. Then we're going to move to a condensed version, then to that sleek zigzag shorthand, and finally we'll land at level 4, which shows us the molecule's true shape in space. We're basically going from total detail to elegant simplicity.
So this is level 1, the complete structural formula. It's the most literal drawing you can make. Every single line you see represents a covalent bond. That's a pair of electrons being shared between atoms. If you look at ethane up there, the single lines are single bonds. Makes sense. Then in the middle, ethene has that double line. That's a double bond, 2 shared pairs. And ethyne, you guessed it, a triple bond, 3 shared pairs. Nothing is hidden here.
All right, time for our first simplification. We're going to start cleaning things up, moving from a detailed pictures to something that looks a lot more like a line of text. This is all about being more efficient without losing any crucial information.
Okay, so check out how this works. It's really logical when you see it step by step. You start with the full drawing. First, you just erase the lines for the bonds between carbon and hydrogen. Then, you squish the whole thing down into a single line, grouping the hydrogens with the carbon they're attached to, like CH3 or CH2. The last little trick for really long chains is to group any repeating parts. See those 6 CH2 groups? We just pop them in parentheses with a little 6. So much cleaner.
All right, this is the big one, level 3, the bond line structure, the zigzag. This is what organic chemists use every single day. It's super fast to draw, it's clean, and once you know the rules, it's incredibly powerful.
To read these things, you just need to know 4 simple rules. First, the lines themselves, the zigzags, they represent the bonds between carbon atoms. Second, any junction, a corner, a vertex, anywhere 2 lines meet, that's a carbon atom. Third, the end of any line, a terminal point, that's also a carbon, specifically a methyl group. And fourth, and this is the magic rule that makes it all work, carbon always wants to form 4 bonds. So we just assume there are enough invisible hydrogens on each carbon to get it to that magic number 4.
Let's just hammer these rules home one more time because they're super important. Rule 1, the lines are the carbon-carbon backbone. Rule 2, every corner and intersection is a carbon atom. Rule 3, the end of any line is a methyl group, a CH3. And Rule 4, the golden rule, carbon always makes 4 bonds. So if you look at a carbon at a corner and you only see 2 lines coming off it, you just know, there are 2 invisible hydrogens there to make up the difference.
This is the perfect way to think about it. It's like an X-ray. The simple, clean drawing on the left is what a chemist sees and draws, but what their brain understands is the full picture on the right, with all those hidden carbons and hydrogens revealed. It's a shared secret, a hidden layer of information that everyone just agrees is there. So you might be wondering, what about atoms that aren't carbon or hydrogen? We call those heteroatoms. And the rule here is super simple. They are never invisible, ever. If you've got an oxygen, a nitrogen, a bromine, whatever, you have to write its symbol out. You can see it there with the OH for the alcohol and the N for the nitrile. No hiding allowed for those guys. And get this system is so elegant, it makes drawing rings ridiculously easy. A triangle? That's cyclopropane, 3 carbons in a ring. A pentagon is cyclopentane,
5 carbons. And that hexagon, probably the most famous one in chemistry, is cyclohexane. Each corner is just another carbon atom following the exact same rules we just learned. It's pretty brilliant, right? All right, so you've mastered the condensed formulas, you can read the zigzags, you're feeling pretty good, right? Well, I gotta break some news to you. Everything we've looked at so far is based on a lie. A very useful lie, but a lie nonetheless.
And here's the problem. Paper's flat. Your screen is flat. Molecules are not. They're real, 3D objects. They have depth and volume and a complex architecture in space. So all those drawings we just learned are really just flat shadows of a much more interesting 3D reality.
Which brings us to a huge question, doesn't it? If we're stuck drawing on a flat surface, how can we possibly do justice to a molecule's true 3D shape? How do we show that some parts are coming forward and some are going back?
Well, chemists are a clever bunch. They, of course, came up with a system for that, too. A way to bring these flat drawings to life and show their true three-dimensional structure. And this is the trick: wedge and dash notation. Just imagine your screen is a flat plane. Any normal, plain line means that bond is lying flat on the screen. Now see that solid dark wedge? Think of that as a bond popping out of the screen, coming right at you. And the dashed wedge? That one's going behind the screen, pointing away from you. Simple, right? It's a code for depth.
But of course, to really get a feel for a molecule's shape, we have to go beyond drawings. That's where models come in. On the left, you have a framework model, which is kind of like a wire skeleton. In the middle is the classic ball and stick model showing both the atoms and the bonds. And on the right, you have the space-filling model, which gives you the best sense of the molecule's actual size and surface.
This table breaks it down perfectly. Each model has a job. The framework model is awesome for seeing the pattern of bonds, but it hides how big the atoms are. Ball and stick is great for seeing the geometry, but it doesn't really show you the molecule's true volume. And the space-filling model is the best for understanding the overall physical bulk, but it hides all the bonds inside. It's all about choosing the right tool for what you want to see.
So, let's bring it all home. We've gone from messy, detailed drawings all the way up to elegant 3D models. We've basically just built a complete toolkit for drawing and understanding molecules.
And this is the most important takeaway. It's not that one of these methods is better than another. They're just different tools for different jobs. You use the complete structure when you're first learning. You use condensed when you're writing a quick formula. The bond line is the professional's go-to for sketching, and the 3D models are absolutely essential when you need to understand how a molecule is really going to behave in the real world.
And that's it. You can now read the chemist's secret language. You can look at a simple zigzag and see the complex, three-dimensional reality hiding underneath. And that's a superpower, because a molecule's shape is everything. It determines what it does. So the only question left is, now that you can read the blueprints of life, what will you decode next?